let's first talk about types of descriptive statistics called frequencies and frequency distributions. So what is a frequency? Well, it's the number of times that a value of a variable occurs. So, if there's 25 redheads in a group, their frequency of redheads is 25. A frequency distribution is the number, a distribution of the number of times that each value of a variable occurs in the distribution. So it is basically a distribution of frequencies for a variable. So when you do frequency distributions in SPSS, you get some other goodies. So you can see here's the header. So we get percent, and percent is just the percent of cases that have each value of the variable. So if that there's 100 folks in the class, 24 have red hair, that would be 24%. The valid percent usually is the same as percent. It is the percent of cases that have each value of the variable of those who actually had a value. So it excludes folks who didn't respond or gave a missing response, so something that didn't work or you couldn't categorize. So the valid percent is the percent of those who gave a valid response, whereas the percent is the percent of all responses, period, whether they were valid or not. Finally, cumulative percent is the percent of cases that had a value that was that level or lower. So the cumulative percent, for example, of 28-year-olds would tell you the percent of folks who are 28 or younger. And so it's actually one that students have problems with, so I'll go over. So this is the frequency distribution of the undergrads in my last Intro to Stats course at Sac State. So what you have here is their ages. So these are the possible values of ages that were in the class. They range from 20 to 45. Note that not every value occurred. So like there was no 39-year-old, for example, it just goes from 38 to 40. So it is the range of values that actually occurred is what SPSS gives you, not the range of possible values. The first column is the actual frequency. So it's, there were 10 21-year-olds, for example. So how many folks had each value of this variable, which is age. Percent is exactly what it sounds like. It's the percent of folks who were each age. Valid percent in this case is exactly the same because everyone provided a valid age. They would differ if someone forgot to give their age or gave me a joke age, etc. Finally, the cumulative percent is that column I was saying is the percent who have a value or lower, okay? So it's the percent of observations at or below a particular value that occurred. And so let's try this out with a couple questions. So how many 25-year-olds were there in my class? So go to the line that's 25 and how many is asking for you frequency. So 25, there were 5 of them, right? 5 of them. Boom. So what percent of the class were ages 20 to 24 years old? So we want to know what percent were 20, 23, or 24, right? So the easiest way to get that is go to the percent column, and you see there's 15% who were 22, 10% who were 23, and another 10% who were 24. Add those together, you get 35%. What percent were 24 or younger? So now we're going to use the cumulative percent column, right? So find the row for 24, go all the way over there. It's 55.0 is what it says on the cumulative percent column for 24, age 24. That means 55% of my class were age 24 or younger. That's what that means. That's what cumulative percent tells you, is a percent who are that value or lower, right? In this case, it's age, so it's 24 or younger. And what percent of the class were older than 35? Wait a minute, that's not as easy to get. So there's a couple ways to get it. The easiest way to get it is to use cumulative percent again. So if you go over to the row for 35 and go all the way to cumulative percent, you see that 83.3% of the class were 35 or younger. So what percent were older than that would be 100 minus the cumulative percent. So it'd be 100 minus 83.3 is going to give you 16.7%. So 16.7% of my class were older than 35. So your grandma tells you she got a 76 on the Rate Your Hotness survey that an old friend sent her on social media. So is your grandma hot or not? Well, there are three things you need to know in order to make sense of the individual score that someone gives you. I mean, 76 is just sort of out there, right? Is that high, low? What's the range? Is it, 0 to 100, or is it like up to, 5,000? And we have no idea. So this is what you need to know in order to interpret grandma's hotness score. One is the shape. So you need to know whether the distribution is normal or skewed. We're going to talk about each one of these a little more. You need to know central tendency. And central tendency is what is sort of the most typical score in a distribution. What's the most commonly occurring value in a distribution? We call that central tendency, where they tend to cluster. And finally, how spread out are they? That's variability and dispersion. Did everyone get the same score or almost the same score, or are they really widely spread out? So shape, central tendency, and variability / dispersion, whichever term you like. So in terms of shape, we want to know whether the distribution of scores is normal or skewed. So here's three different distributions. That one on the far left is what we call normal or symmetrical. It's a mirror image from left to right down that middle line. The distributions that are to the right are negative skew and positive skew. They are not bell-shaped. They have a long tail. So the way I remember negative versus positive skew is I think of the number line from back in elementary school. Number line started in the middle with 0, and to the left was negative, and to the right was positive. And so if the tail of the distribution goes to the left, it's negative skew. If the tail goes to the right, that's positive skew. So let's first talk about symmetrical distributions. They're also called normal. So this is what we want to characterize, or bell-shaped is another term that's used for them. And it turns out that in a lot of things about people are normally distributed. So height, weight, and intelligence are normally distributed in a big enough population. And it turns out that the mean, median, and the mode are all the same. So look at that little plot over on the right where you got a bar in the middle, and it says symmetric. The mean, median, and mode are all the same. So we're going to learn what those are in a sec, but it is important. Negative skew is that plot that's in the middle of the screen up top. Negative skew has a tail to the left, or sometimes it's called left skewed. So scores on an easy midterm would be like this. Most people get high scores, but there's still a few people who blow it just because they didn't sleep or had a bad night or didn't study, whatever it is. So even on an easy test, there's still people who blow it, but most people do well. That would be a negatively skewed distribution. So in these distributions, in all skewed distributions actually, the mean gets pulled towards the tail. So the mean will be, in negative skewed ones, lower than the median. So it gets pulled towards the tail, and so it gets pulled down. Positive skew is the opposite of that, where you've got a tail to the right, or right skewed. So housing prices are like this. So most folks have houses that are somewhere between $250,000 and $500,000. But then the distribution just sort of trails off for a long time because you got millionaires and billionaires and folks who have very, very expensive houses. So that would be positive skew. That would be the graph on the right up top. So it turns out, again, the mean gets pulled towards the tail. So the mean is going to be higher than the median in positively skewed distribution. And this is why, for example, they don't do mean housing prices, they do median housing prices, because the median doesn't get yanked quite as high towards the tail. So is age skewed or normally distributed? That's the first thing we want to know is the shape. And this is the way we used to do things in this class, where we do a histogram with a normal curve superimposed, and you'd kind of guess. How are we supposed to know? That was something it took me a while to learn, that not everyone sort of saw things the same way. I mean, if anything, this kind of looks like it has a tail to the right, right? It looks positively skewed. But how are we supposed to know? Or at least how are we all supposed to reach the same conclusion fairly? So in this class, I don't make you guess at looking at pictures. We use something called the skewness statistic. You can get it in frequency in a couple other places. SPSS calculates it, and basically you use a rule to tell, is my distribution skewed or not? So the rules for interpreting the skewness statistic, again, there's those three distributions. First of all, if the skewness statistic that SPSS calculates is just 0 across the board, that means that your distribution is perfectly normal. Okay, so that doesn't happen very often, but it's just sort of an idea, or at least didactically. The closer it is to 0, the less skewed a distribution is. If the absolute value of your skew statistic, that is, ignore the sign, if it's less than 2, so I tell you here that would be between negative 1.999 and positive 1.999. That would be less than 2 absolute value. So your distribution is not perfectly normal or symmetrical, but you know what? It's close enough for you to say, yeah, it's basically normal. It's not skewed enough that I need to worry about it. So we say it's basically normal. And this is nice because you can do all the normal stats as long as your data aren't too skewed. So again, if your skewness statistic, the absolute value of it is less than 2, you would say that my distribution's basically normal, or normal enough, something like that. So what does skew actually look like? Well, if you have an absolute value of your skew statistic that is 2 or bigger, so either negative 2 or is technically smaller, but we're doing absolute value, or positive 2 or bigger, you've got skew. You got a problem. So that means not only is it not normal, it's very skewed. And so you want to look at the sign to determine is it positive or negative skew. If it's a negative sign, you've got a negatively skewed distribution where the tail's to the left. If you have a positive sign and it's 2 or bigger, you've got positive skew with a tail to the right. So again, look at the skewness statistic and take the absolute value, so ignore the sign. If it's less than 2, no worries. If its absolute value is 2 or greater, you've got a skewed distribution. Look at the sign. If it's negative, negative skew, no negative, which just means positive. It doesn't print positive signs, you've got positive skew. So let's go back to age again from my intro class. And this is SPSS spitting out stats for us, and that is the skewness coefficient. So is age skewed or not? There's our rules again. Again, we're looking to see is the absolute value of that 2 or bigger. So it's already positive. So is 1.2 bigger than 2? No, it's not. So what would our conclusion be? Well, our conclusion would be normal enough. That's what we'd say. Because the skew statistic, absolute value, is less than 2, the ages are basically normal. That's what we would say. Okay, that's what I want you to say on your homeworks and tests, etc. It's good enough for us to just pretend it's not skewed. So the next thing we need to know to interpret grandma's score is central tendency. Again, that's just sort of what's the common score in the distribution, or what's the most commonly occurring score. So what was the typical age of students in my final intro to stats class? There are three different ways to answer this question, three different measures of central tendency. They are the mode. The mode is the most frequently occurring value in the distribution. So it's just it would be for my ages, the age that occurred most frequently. So the other measures of central tendency do more with the data than the mode, because the mode is just saying, look, that was the most common age. It doesn't take into account things like the magnitude of differences, etc. So it's just like, what's the most frequently occurring age? So a little bit better is the median. The median is the score, or in this case, age for the class that divides the distribution into 50-50. So 50% are lower than the median, 50% of scores are higher than the median, or in this case, ages. So it's not sensitive to outliers, which is a good thing. So if you've got a skewed distribution or you've got some just really funky values, that's what an outlier is in your distribution. The median doesn't change much, I guess, because again, it doesn't take into account sort of the absolute magnitude of differences between things. It is just the score that's literally in the middle of the scores. Okay, it's the one in the middle of the distribution. So finally, we have the mean, and this is the average. So this is what we typically think of as the average, the arithmetic average of the distribution. So what was the average age? It's the age or score that minimizes the distance between it and all other scores in the distribution. And it provides the most information about the underlying distribution, all values in it. So it is sensitive to magnitude, which is both what makes it awesome and also what makes it problematic if you've got skew. So let's talk about the mode. The mode is just the most frequently occurring value in a distribution. So here is for the ages in my class. You can find the mode. It's 21. 21 was the most frequently occurring age in my intro to stats class. So you would say that sort of formally the modal student age was 21 years old. So you can have more than one mode in a distribution. You can have more than one, for example, most commonly occurring age. And so it's one of the reasons that the mode is not very useful a lot of times. So if you have two modes or two values with the most high frequency, you've got a bimodal distribution. If you've got more than two, we call it multimodal. So again, the other measures of central tendency provide more useful information, and you want to use them if you can over the mode. Okay, so you want to use the median or especially the mean if you can, because they use much more information about the underlying values in the distribution. However, the mode is the only measure of central tendency you can use for nominal data, and they don't usually, they just say, you know, the most frequently occurring, you know, hair color was this, right? That would be the mode. So you wouldn't calculate, for example, the median college major or the mean ethnicity. Those are both median values. You'd say the majority of the distribution or the most common college major was this, or the most common ethnicity was this. You'd be talking about the mode. So it is the best measure of central tendency for nominal data. It's the only one, to be honest. So this is a question that will be repeated, because I found that folks miss this, even though I say, hey, this is going to be on quizzes more than once. You ready? What is the modal sex of that class? So there they are. There was 17 males and 43 females. So the answer is not 43. The answer is female. So n here is the number of times that a value occurred. The mode is what the value was. So there was 43 females, so the modal age was, the modal sex was female. So moving on to the median. Again, the median is the score that divides the frequency of values into halves. Okay, so 50% below it, 50% above it. Again, here's SPSS doing it for us, and 24. So half the class was younger than 24, half the class was older than 24. So it is the value that's at the 50th percentile, which is also sometimes called the second quartile, or Q2. And the median is based on the number of values, not their magnitude. So it does not take into account um, how different scores were, just how many scores there are. This is the score, in our example, age, in the middle of the distribution. You could add a 99-year-old and it doesn't even change that much. The mean would go crazy. So it doesn't capture the magnitude of the values. And the median can't be used in most of the fancy inferential statistics that we want to use for our dissertation. So the mean is preferred when you can use the mean. So it is insensitive to outlying scores or the shape. So even in skewed distributions, you can use the median instead of the mean. When you have interval or ratio data that are very skewed, so again, like housing prices or salaries, they'll typically use the median instead of the mean because the mean gets pulled towards the tail. The median is, right in the middle regardless of the shape of the distribution. So the median is the best measure of central tendency for ordinal data. So remember that. So mode is for nominal, median is the best for ordinal. Finally, we have the best measure of central tendency when you can use it is the mean. So the mean is the value that mathematically balances the entire distribution. It is the average. Here's SPSS is telling us that the average age of my students was 26.77 years. So average age was 26, roughly 27, fine. So it captures the magnitude of the values. So unlike the median or the mode, it actually provides more information about all the values in the distribution. Just a change of just one value can change the mean a lot. So that's what makes it good and what makes it bad. It's very sensitive to all scores in the distribution. But what that means, because it's sensitive to all scores in the distribution, is it gets yanked towards the tail of skewed distributions. So its sensitivity to all scores is both its strength and weakness. So real estate prices are positively skewed, as we discussed, and so median prices are reported instead of means because the median tends to be more towards what a typical house actually sells for, whereas the mean gets yanked up towards Bill Gates' house or whatever. So the mean is the best measure of central tendency for interval or ratio data, as long as the distribution is not very skewed. That is, as long as the skewness coefficient we talked about earlier doesn't have an absolute value of 2 or bigger, you can use the mean. So it's the best measure of central tendency for interval or ratio data if your distribution is normal. If it's not normal, if it's very skewed, use the median instead of the mean. So the median is kind of your backup if your distribution ends up being very skewed or has crazy outliers for interval or ratio data. So that is central tendency. Let's talk a little about variability. And folks have trouble sort of understanding, like, why do I care? I just want to know what a typical score is. But variability is important, and I'll show you. So variability or dispersion tells you how much the values varied from each other in the distribution, how spread out they were. Were they really clustered in the middle, or were they widely dispersed? So how spread out were the ages of the students in my last intro to stats course? There are 4 different ways to answer this. So there's the range. The range is, technically it's just the difference between the highest and lowest scores in a distribution. It's what's that range, subtract them. Again, like the mode, it's not that great of a measure of dispersion. So the other ones provide more information. This is really affected by even one score and doesn't use sort of magnitude of differences very well. So the range isn't that great. So the next most sophisticated measure of variability is called the semi-interquartile range, or the SIR. The SIR is half of the difference between the first and third quartiles. So you find the score at the third and first quartiles, you subtract and divide by 2, and that is something called the semi-interquartile range. It is insensitive to outliers or the shape of the distribution, so that's one thing that makes it good. But it's not as good as the standard deviation when you can use it. So the standard deviation is sort of like the mean of the spread of the scores. It's the average amount that scores differ from the mean. So the standard deviation provides the most information overall about all values in the distribution, and so it provides the most information for your analyses. So you want to use the standard deviation if you can. Now finally, I have to bring up the variance. Variance is goofy. It's the squared standard deviation is what it is. So it's the average squared amount that values differ from the mean. So I have to bring it up because later on we're going to be doing something called analysis of variance, and I need you to know sort of what's a variance. All right, so here's two distributions. They have the same mean, so how are these two distributions different? Well, the red distribution is pretty tightly clustered around that mean of 70, whereas the blue distribution still got a mean of 70, but the scores are way more spread out in that distribution. So again, this is why measures of variability are important in addition to what was the typical score, that is your measures of central tendency. So they both have a mean of 70, but they have different variability. Distribution A, the scores are really tightly clustered around the mean. Distribution B, the blue one, they're much more dispersed. So your grandma's sort of hotness score of 76 suggests she's much hotter in distribution A, right, than distribution B, because there are fewer high scores in distribution B. So that 76 is 6 points above the mean. That's way less likely to happen in the red distribution than the blue one. So the first measure of variability we're going to talk about in detail is the range. Again, it's just the difference between the highest and lowest scores in the distribution. That's all it is. So SPSS calculates it and tells us 25. There's a 25-year range in the ages in my class. So specifically, if you go back and look at the frequency distribution, it ranged from 45 to 20. So 45 minus 20 is 25 years. That's your range. So larger values do tell you that a distribution is more spread out. It is one number, but sometimes, particularly in like the media, they'll give the endpoints, ages range from 20 to 45 rather than doing the subtraction. That's fine. Instead of just giving the one number. It is a very crude measure of dispersion, and it doesn't provide a whole lot of information about how much the score is really spread out. Like you can add just one crazy high score and it changes the range a lot. It also doesn't really allow you to interpret individual scores very well because it's insensitive to magnitude of differences. And again, it's easily affected by having even one score. So in this class, for example, if I was to add just one 75-year-old, suddenly we have a range of 55 instead of 25. It's over twice as big. And so it seems to suggest that the scores are way more spread out than they really were, with just one outlier. However, it is the only measure of variability you can use when you've got nominal data. So specifically, and note this, when you've got nominal data, you would use the mode and the range endpoints, that is, for nominal data. So you'd say the most common hair color was redheads, but it ranged from bald to gray, sort of thing. The next measure of variability that is a little more complex quantitatively is the semi-interquartile range. And again, it is 1/2 of the difference between the first and third quartiles. So SPSS gives us our percentiles, and the first quartile is the 25th percentile. The third quartile is the 75th percentile. So 30.5 minus 22 divided by 2 is going to be your semi-interquartile range, and that is 4.25 years. So that is a measure of how spread out the scores are. Instead of 25, we'd say sort of 4.25 years. It was the semi-interquartile range. So what is a percentile rank? Percentile rank is the percentage of scores that fall below a value. So 25% of scores fell below 22. 75% of scores fell below 30.5. there are 3 common percentiles. They are the quartiles. So Q1, 2, and 3 are the 25th, 50th, and 75th percentiles. And again, that's the actual formula for your semi-interquartile range is Q3 minus Q1 divided by 2. And again, larger values of a semi-interquartile range tell you that your distribution is more spread out. It's a little bit better than the range, but it's still not that great in terms of variability. It does have a cool sort of function associated with it, is if you take the median and you add one semi-interquartile range and you subtract one semi-interquartile range from the median, it will be the middle 50% of distribution of scores. It is best used when you've got ordinal data or you've got very skewed interval or ratio data. So again, the median and the semi-interquartile range are what you would use as your measures of central tendency and variability for ordinal data, or you would use those two things for interval/ratio if it was super skewed. So the standard deviation is the most common measure of variability. It's the average amount that scores or values deviate from the mean in a distribution, and it's in original units. So here's SPSS calculating it, and the standard deviation was 6.796. So that's about 6.8, right? So the average amount that scores deviated from the mean of 26.8 up there was about 6.8 years. That's what you would say. So larger values of the standard deviation indicate that a distribution is more spread out, has more variability. Heterogeneous distributions have large standard deviations. That is, where the scores are very different from each other, the ages, they have big standard deviations. And ones where the scores are very similar, they tend to have small standard deviations. So we call that homogeneous. So standard deviation is great because it captures the magnitude of values in the distribution, how much they differ from each other. So it does give you the most information about the values in that distribution. So in a symmetrical distribution, it turns out some cool things happen with the standard deviation and the mean. If you do the mean plus and minus one standard deviation, that's the blue in that plot that's showing, that will be about 68% of all values in the distribution. The mean plus and minus 2 standard deviations, that's the edge of the green lines in that distribution that's showing. The mean plus and minus 2 standard deviations is going to be the middle 95% of all scores if that variable is normally distributed. And finally, the mean plus and minus 3 standard deviations, that's 99% of all scores. So this is going to become relevant when we talk about z-scores and later on probability. So the standard deviation is your preferred measure of variability for interval or ratio data. As long as that distribution isn't too skewed, you can use the standard deviation along with the mean for interval or ratio data. If it's very skewed, you would use the median and the semi-interquartile range. So finally, we got the variance that I just kind of have to throw in because we're going to run into it. So it's the average amount that scores deviate from the mean in squared units. So squared years, for example. So here's the variance, the 46.182. If you take the square root of that, you get the standard deviation. But on average, the scores differed from the mean by 46.182 squared years. It's just, who cares, right? So larger values do indicate that distribution is more spread out. It's just a standard deviation in squared units. That's all it is. It's not really used as a measure of variability per se. I need you to know it for a couple reasons, but one of them is I need you to know you take the square root of it and you get the standard deviation, because some of the stats, the fancier stats we do, give you the variance in the output instead of the standard deviation, so you need to know that, hey, I just take the square root of it. So that's the whole reason that I had to make sure to cover it. All right, so to get the standard deviation, just take the square root. or the variance, and then I'll do it for you. So if you did that with the 46.182, you get the 6.796. That is the standard deviation. We're going to be doing analysis of variance or ANOVA later, so this at least you'll know it's a variance is a measure of how spread out. So finally, I want to talk about box plots. So box plots are these plots that SPSS makes that quickly sort of summarize a lot of information. They show you the minimum score in a distribution, Q1, again, the 25th percentile. The middle score in a distribution, that is the median or 50th percentile. Q3, which is the 75th percentile, shows you the max score, and they also show you sort of crazy scores, that is outliers. So here is the distribution of ages for men and women in my intro class with a box plot. And the sort of top to bottom width of the blue boxes here are the top is the Q3 and the bottom is Q1. So it is the 75th and 25th percentiles. But importantly, that black line in the middle is the median. So that is the middle score in the distribution. So it looks like the average ages were very similar. If you look at the two black lines, they're really close to each other, the average age of men and women. So these little whisker things on the end here that I highlight in yellow, these are the furthest scores in the distribution that are not outliers. So these are how spread out things were without getting crazy. These green dots out in the middle of nowhere for the males, these are outliers. These are scores that were very different from the others in the distribution. So the box plot shows you that they're outliers because they're way beyond the whiskers, and it gives you the actual numbers. So that was case 23, 7, and 38 were much older than the other males.